In February 2017, the NASA made an announcement that fundamentally shook the foundations of modern astronomy. Located just 40 light-years away in the constellation of Aquarius, researchers identified what was immediately hailed as the Holy Grail of exoplanetary science, the TRAPPIST-1 system. Unlike previous discoveries of isolated, uninhabitable gas giants, this system revealed not just one, but 7 Earth-sized worlds orbiting a single, cool, red star. Even more significantly, 3 of these planets were positioned perfectly within the habitable zone, the precise Goldilocks region, where temperatures theoretically allow water to exist as a liquid. However, recent actions by the James Webb Space Telescope have cast a shadow over this initial optimism. For the last 2 years, the telescope's mirrors have been trained on this system, looking not just for planets, but for atmospheres. The data returned is forcing the scientific community to confront a sobering reality known as the Red Dwarf Paradox. The findings suggest that the very stars we thought were cradles for life may actually be cosmic traps. To understand why this matters, we must consider the broader context of our galaxy. Red dwarfs, or M-dwarfs like TRAPPIST-1, are not merely a curiosity. They are the dominant stellar population, making up 75% of all stars in the universe. Because they burn their hydrogen fuel slowly, they live for trillions of years, providing ample time for evolution. The prevailing logic has long been that if Earth-sized planets are common around these ubiquitous stars, then the universe must be teeming with life. But logic breaks down when faced with empirical data. To fully appreciate the gravity of the current findings, we must first revisit the moment the TRAPPIST-1 system captured the world's attention. In February 2017, NASA released data that seemed to fundamentally alter the trajectory of exoplanetary science. Located just 40 light-years from Earth in the constellation Aquarius, astronomers had identified a system that was unprecedented in its architecture. Unlike the solitary worlds or gas giants that had dominated previous catalogs, this system contained 7 Earth-sized planets orbiting a single star. Even more remarkably, 3 of these worlds were situated precisely within the habitable zone, the orbital region where temperatures theoretically allow for the existence of liquid water. At the time, the discovery was viewed as the most significant breakthrough in the search for life beyond our solar system. The narrative was driven by a compelling statistical argument involving the host star itself. TRAPPIST-1 is a red dwarf, technically classified as an M-dwarf. These are not rare anomalies. They are the most common stellar objects in existence, comprising approximately 75% of the entire stellar population of our galaxy. Furthermore, while our own Sun is roughly halfway through its 10 billion-year lifespan, M-dwarfs burn their fuel with extreme efficiency. They are capable of shining for trillions of years, providing a time window for biological evolution that exceeds the current age of the universe by orders of magnitude. The scientific logic following the 2017 announcement appeared flawless. If Earth-sized planets are common around these ubiquitous, long-lived stars, then the probability of life arising elsewhere should be overwhelmingly high. It was a numbers game, and the odds seem stacked in favor of a populated universe. However, to understand why this optimism is now being challenged, we must look at the specific engineering of the TRAPPIST-1 system, which differs radically from our own solar neighborhood. The host star, TRAPPIST-1, is a fraction of the size of our Sun. In terms of physical dimensions, it is barely larger than the planet Jupiter and much cooler than the yellow dwarf star that sustains life on Earth. Because the star is so dim and cool, the habitable zone is pulled inward to an extreme degree. To receive enough heat to sustain liquid water, the planets must orbit in dangerously close proximity to the star. To visualize the scale of this system, consider that the entire 7-planet assembly fits comfortably within the orbit of Mercury. These worlds are not leisurely orbiting at a safe distance. They are huddled around a faint stellar ember. This proximity introduces gravitational and radiation variables that we simply do not experience on Earth. While the location satisfied the thermal requirements for the Goldilocks zone, astronomers knew from the beginning that proximity comes at a price. As we move into the technical analysis, we see that this closeness creates a gravitational gradient so severe that it fundamentally alters the physics of the planets themselves. The first major engineering hurdle that challenges the habitability of these worlds is a direct consequence of their orbital mechanics. Because the planets of the TRAPPIST-1 system orbit so close to their host star to maintain thermal equilibrium, they are subjected to intense gravitational gradients. Over millions of years, this gravitational friction has forced the planets into a state known as synchronous rotation, or tidal locking. This is the same physical mechanism that keeps our moon constantly presenting one face to Earth. But when applied to a planet capable of hosting life, the implications are far more severe. In a tidally locked system, the concept of a day-night cycle ceases to exist. The planet is permanently bifurcated into two distinct hemispheres. One side faces the star in an eternal scorching noon, while the opposing side remains frozen in a perpetual starlit night. This is not merely a quirk of the calendar. It is a fundamental constraint on the planetary climate. For a biosphere to function, the planet's atmosphere must act as a massive heat engine, transporting thermal energy from the irradiated day side to the frozen night side. This creates a reliance on atmospheric circulation that far exceeds the requirements of Earth's weather systems. This dynamic introduces the risk of a catastrophic failure mode, known as atmospheric collapse. On Earth, our rapid rotation and Coriolis effect help distribute solar energy relatively evenly. On TRAPPIST-1b or 1c, the atmosphere must aggressively circulate heat to prevent the dark side from reaching cryogenic temperatures. If the atmospheric currents are not efficient enough to redistribute that heat, the gas on the night side will cool rapidly. Eventually, the temperature drops below the freezing point of the atmospheric compounds themselves. The atmosphere begins to liquefy and then freeze solid, effectively snowing out onto the surface. This creates a pressure vacuum that pulls more air from the day side to the night side, feeding a runaway cycle until the entire atmosphere is sequestered as ice on the dark hemisphere, leaving the planet suffocated in a vacuum. Even if an atmosphere is robust enough to prevent this collapse, it faces a second external threat: the volatility of the star itself. While red dwarfs are known for their longevity, their early developmental stages are characterized by extreme instability. Unlike our G-type sun, which is relatively magnetically quiet, young M-dwarf stars are prone to violent outbursts. NASA data indicates that these stars frequently emit stellar flares with energies hundreds of times more powerful than the strongest solar flares ever recorded in our own solar system. These events subject orbiting planets to a relentless bombardment of high-energy X-ray and ultraviolet radiation. For a planet located 93 million miles away, like Earth, this might be manageable with a strong magnetic field. However, for worlds huddled within a few million miles of the source, this radiation acts as a persistent erosive force. This process, often described in aerospace engineering as stellar wind stripping, functions like a cosmic sandblaster. The high-energy protons strike the upper atmosphere with enough kinetic energy to break molecular bonds and accelerate gases to escape velocity. Over billions of years, this mechanism can physically ablate the atmosphere, stripping away hydrogen and oxygen faster than the planet's volcanism can replenish them. Mathematical models suggest that without exceptional shielding, a planet in this environment is likely to be reduced to a barren, irradiated core long before life has a chance to take hold. For years, the debates surrounding tidal locking and atmospheric collapse remained largely within the realm of theoretical physics. We relied on computer models and mathematical simulations to predict the conditions on these distant worlds. However, the operational deployment of the James Webb Space Telescope has fundamentally altered this landscape, allowing us to transition from theoretical modeling to direct empirical observation. Specifically, the mid-infrared instrument, known as MIRI, provided the engineering capability required to conduct a thermal census of the TRAPPIST-1 system. To understand the significance of these findings, it is necessary to understand the method used to acquire them. MIRI utilizes a technique known as secondary eclipse photometry. Because the glare of the host star is overwhelming, we cannot simply take a photograph of the planet. Instead, astronomers measure the total light emitted by the entire system when the planet is positioned beside the star. They then compare this baseline to the moment the planet slips behind the star. The minute drop in brightness detected during that eclipse represents the infrared light, essentially the heat emitted by the planet itself. This requires a level of precision that was previously unattainable in aerospace engineering. The first target for this rigorous analysis was TRAPPIST-1b, the innermost world of the system. Prior to the Webb observations, there was significant hope within the scientific community that this planet might possess a dense atmosphere, perhaps rich in carbon dioxide. Such an atmosphere would act as a planetary blanket, redistributing heat from the day side to the night side and moderating the extreme surface temperatures. However, the data returned by the MIRI instrument painted a starkly different picture. The instrumentation recorded a dayside temperature of approximately 450 degrees Kelvin, or roughly 230 degrees Celsius. From a thermodynamic perspective, this reading is critical. It matches almost perfectly with what physicists call a blackbody model, the theoretical heat signature of a bare rock with zero heat redistribution. If an atmosphere were present to circulate the warmth, the dayside temperature would be lower. The absence of this cooling effect indicates that TRAPPIST-1b is likely a dark, scorched world, stripped down to its geological crust, with no air to shield it. Following this disappointment, attention shifted to the next planet in the sequence, TRAPPIST-1c. Because it orbits further from the star, models suggested it had a higher probability of retaining its volatiles. Many hoped it would prove to be a Venus analog, possessing a thick, crushing atmosphere that could withstand the stellar environment. Yet, when MIRI analyzed this second world, the thermal emission data was equally conclusive and equally bleak. The results suggest either a bare rock surface or an atmosphere so tenuous that it is scientifically negligible. These consecutive findings provide powerful validation for the stellar wind erosion hypothesis. The data suggests that billions of years of high-energy proton bombardment from the red dwarf star have acted like a cosmic sandblaster. This process appears to be eroding the planetary atmospheres molecule by molecule, stripping away gases faster than any potential volcanic activity could replenish them. From an engineering standpoint, this defines a critical failure mode for habitability in M-dwarf systems. A planet may reside in the thermal habitable zone, but without a magnetic field strong enough to deflect this stellar wind, it cannot sustain the atmospheric pressure required for liquid water to exist. We have now examined the TRAPPIST-1 system through the dual lenses of orbital mechanics and thermal engineering. The data returned by the James Webb Space Telescope leads to a preliminary yet sobering conclusion regarding our search for life. The observations of the innermost planets, TRAPPIST-1b and 1c, strongly indicate that they are devoid of significant atmospheres. This empirical evidence validates the hypothesis that red dwarf stars, despite being the most common stellar demographic in the galaxy, may function effectively as cosmic sterilization devices rather than incubators for biology. The violent radiation environment characterized by these stars appears capable of stripping away the essential gaseous shields required for habitability, leaving behind barren rock. However, the scientific analysis of this system is not yet complete. While the inner worlds appear to be dead, aerospace exploration efforts are now pivoting to the outer worlds, planets D, E, and F, which reside squarely in the traditional habitable zone. Because these planets orbit further from the host star, they receive a lower dose of ionizing radiation and may have successfully retained their volatiles. Yet, even if these atmospheres survived the initial stellar bombardment, any potential life would face extreme environmental constraints. Current astrobiological models suggests that habitation on these tidally locked worlds would likely be confined to the terminator zone. This is the thin, permanent ring of twilight separating the burning day side from the frozen night side. In this narrow band, temperatures could theoretically remain mild enough to support liquid water. However, the environment would be alien to our understanding of a biosphere. The temperature differential between the hemispheres would drive constant, ferocious winds across the terminator, creating a perpetual storm front. Furthermore, any potential flora would have to adapt to a star that emits primarily infrared light rather than the visible spectrum utilized by Earth's plants. Consequently, vegetation on TRAPPIST-1 would not appear green. Evolutionary biology suggests it would likely be black or deep purple, adapted to absorb every available photon of weak infrared light. Beyond the specific mechanics of TRAPPIST-1, these findings suggest a major philosophical shift in our estimation of extraterrestrial intelligence. For decades, the Drake equation, the probabilistic argument used to estimate the number of active civilizations, relied heavily on the sheer statistical weight of M-dwarf stars. We assumed that because red dwarfs constitute 75% of the stellar population, the galaxy must be teeming with habitable real estate. But the silence from TRAPPIST-1b and 1c points toward a concept known as the Great Filter. It is becoming increasingly probable that the emergence of complex life is rare, not because planets are rare, but because stable stars are rare. If the majority of stars in the Milky Way strip their planets of air, then the vast majority of the galaxy is effectively uninhabitable. This forces a re-evaluation of our own G-type yellow sun. Its stability, its lack of violent flares, and the specific distance allowing for planetary rotation may not be standard features. Instead, they may be the specific, rare engineering constraints required for a biosphere to thrive. Understanding the limitations of the TRAPPIST-1 system offers us more than just astronomical data. It provides a critical correction to our cosmic perspective. We have learned that the mathematical precision of a planetary system, its rhythm, its spacing, and its orbital beauty, does not guarantee its habitability. As we continue to analyze the data arriving from Lagrange Point 2, we are accepting a hard lesson in both aerospace engineering and astrobiology. In the search for a second Earth, we cannot simply look for the right planet. We must look for the right star. If you found this technical analysis valuable and wish to support more deep dive content regarding space technology and exploration, I would appreciate your subscription. In upcoming videos, we will explore the engineering challenges of future propulsion systems and the specific physics behind the search for biosignatures on distant worlds. I am curious to hear your perspective on the Red Dwarf Paradox. Given the extreme volatility and atmospheric stripping we have discussed, do you believe the scientific community should continue focusing resources on M-dwarfs, or should we shift our search exclusively to sun-like stars? Please share your thoughtful analysis in the comments below. Thanks for watching. Until next time.